Hello everybody, welcome to another stream. How's it going? So today we're going to be getting on with adding, just really refining the whole BVH API by making a custom allocator so we can allocate more bottom level BVHs and build multiple BVHs, building volume hierarchies. And what else we're going to be doing? Yeah, we're going to be tuning the data structure a bit of the BVH node so it can fit everything we need in there. And yeah, but I just got a bit thrown a bit of a curveball because I updated my machine yesterday, and guess what doesn't work? My NeoVim config has broken, so I'm thinking about just nuking everything because it's pretty crap anyway. It doesn't really provide any improvement on my code base, and it's just so much shit you have to maintain apparently. So let me just nuke a bunch of crap from my NeoVim config and just... The problem is though, is my theming is kind of based on another one, and it depends on tree sitter being good. But yeah, so I've not really been using a lot of this stuff anyway. Yeah, I guess it would be nice to have like a better line thing, but I should just go back to regular Vim. But yeah, I don't want to lose things, you know what I mean? Hey Glorissa, how you doing? Good to see you. You know, any good programmer... I've already got an old one. Get rid of that. Any good programmer backs up their previous config. This is so annoying. But yeah. We're doing the quickest fix in the world, and we'll get back to actually doing some work rather than messing with NeoVim. I haven't messed with stuff for so long, but it's broken on me now. But how you doing, Glorious sir? Good to see you. And how's everyone else doing? How's it going, guys? My NeoVim config has decided to break on me since I did a system update. I don't know why. I've tried updating stuff. So I'm just getting rid of all the crappy add-on packages and going bare vanilla NeoVim for now. But I might as well go back to Vim, to be fair, because all this stuff is just too much. I wish there was a... Maybe I should switch to a different modal editor and try it, give that a go. I need to make sure I don't... Right, here's telescope. Let's get rid of that. Leader. Crap, let's get rid of that. Tree sitter in a bit. Get rid of you. Yeah, these editors. Which editor are you using, Glorious? What do you use? You see, there's those two modal editors out there that I want to give a go. I think there's one written in Rust, and there's another one, I forgot what it was written in. This is how I remember things usually, right? But I would want to give another, like a modern modal editor a go, because I don't like... I like the idea of Vim, and then NeoVim came along, and it's like C++ C, you know what I mean? It's like that, where it's just too much extra stuff. Like, why do I want to maintain a config in text for an editor? It's just crazy. LSP settings. Goodbye LSP, who needs one of them? NeoDev. I ain't a NeoDev. I don't even know what that is, but it's going. LSP. Right, all this compare stuff, who needs to compare? What's all this? I'll leave that one. Right, here's all my Colmac remappings. This is the way. And there we go, back to basics. Now hopefully I just didn't just destroy everything. Alright, what we got here? Color scheme, ascent. Cannot find. Right, so I couldn't find the color scheme, so it's decided to mess up my the whole key configuration I have underneath. Bananas. Yeah, so we need to get rid of a lot of this stuff because this is all like special tree set stuff, right? So goodbye all my stuff. So I need to get Ascent installed. It should be here. No, apparently not. Get it from the web. The way you used to have to do it. Or we should go back to Iceberg, maybe. That's why I switched editor without Turing complete configuration. For the last 6 months, I use this, the focus editor. This is what we need, is clear focus. What is it? Simple, fast. All right, it's got a little command palette. Is that fuzzy? Did I see fuzzy? Ah, this speaks to me. We value simplicity. Oh yeah. You don't require heavy language editor support. Yeah. Oh, it's a Jai guy. I see that Jai in there. Written in Objective-C. Okay, that was a curveball. That was a curveball. Objective-C. Oh no, it's not. Jai. It's written in Jai. What? So GitHub's like, oh yeah, Jai files are 100% Objective-C. All right. A Jai editor. Hmm. Oh my days, CRLF will be converted to LF on save. It's time to move on. Yeah, obviously, but some people might want the other one. I think, like, at the end of the day, why is my laptop just... my laptop's just black screened. I don't even know what's happened to it. You know, I don't think you should, you know, I get it if you read a file and then in memory you turn it into whatever you want. And then when you save it out, you should respect the user's wishes. You know, so yeah, read it in from disk if it's you know, if it's 2 byte per character. Sure, don't keep it 2 byte per character when it's in memory. When you operate it, it'd be in, you know, a different encoding. But then when you save it back out, you should respect the user's wishes. I think that's a bit dumb. But that limitation doesn't affect me though. See, multi-code point Unicode symbols are not supported. This is where you could, I'm pretty sure, just, oh, multi-code. Oh yeah, that makes it easier for rendering. Yeah, that makes sense. So you can't stack all those emojis together. And the code points to make those crazy emojis. It looks interesting. I'll keep this tab open. Right, Ascent. Gimme. Right, how do I get in there? Hang on a minute. Is it in config? I think so. NeoVim. Colors. Not .text file, .vim file. And we're in. So does that load now? Right, it's loading. It's not loading the colors though. Is it got to be like NeoVim with some dodgy plugins or something? What's the dependencies on this one? Should be right. Why can't I set color map, color scheme? What's going on? Right, iceberg. We're going back to iceberg today. It doesn't really look right though. We're not getting like colors here because I don't have tree sitter anymore. Yeah. Bit crazy. Maybe I should just go simple dark, you know what I mean? Since I can't have a color scheme, let's just get that grayscale font by tech. Where is it? Is it by tech 256, I think? Isn't it? There we go. Let's just do this one, because we can't get a color scheme, might as well just... There we go. Gimme, gimme. And then we can just get on with some actual work. Oh, it's already in there. Right. There we go. That seems like that'll do. So let me just edit that near vim config and chuck that in there. We can actually crack on. Is it? Oh, silly me. Yeah, but I don't think the colors will show up properly. Well, when I clicked the... Ah, shit. I see. Where's the color scheme then? It's a file. The description says it's a plugin to allow... Oh. Maybe I found the wrong one. Oh. And no, this definitely was the color scheme though. The name of it. But anyway, I think we're back to some kind of sane editor experience. Right. That was a pain in the butt. I need to switch away from NeoVim sometime. Right, so objective for today. It's going to be pretty cool. I can write down the things I want to do in a little to-do. BVH to-do. So here's the plan. We want to write custom BVH node allocator on CPU. So why do we need one of these? Or what are the sort of things that we need it to do? It unfortunately needs to be a variable size, but that's not a big issue. So we need a good defragger, right? Defragger, right? How I'm planning on doing a defragger is just basically copying memory around every frame if need be. So we can always So we can reduce fragmentation, so we can maximize the, yeah, it's not a big deal. So we need a good defragger. What else do we need it to do? Yeah, we'll figure out as we write it. And then also, the other plan for today is to kind of like, we need to allow support for mid-level BVHs. So I don't know if you remember, we added a bottom level BVH, and then we're doing there we go. And then we want to do a top level BVH. So a top level, its leaf nodes are a bunch of bottom level BVHs. So the basic idea is I want to have for this game is essentially like a tile map, but it's like the map is made out of tiles. Good way of doing it, just drawing it out, it's just believable. So we're gonna have like a tile map in 3D, but I don't think I want it to be. So I think these individual tiles are gonna have made out of ellipsoids or whatever, and show some. But I think we might pre-make these tiles into a bottom level BVH each. And they're made out of so many ellipsoids, right? But it doesn't matter. These ones are gonna, each of these tiles will probably get updated every single frame, because they'll probably animate a bit. But what I don't want to do, but what I'm thinking about doing, so if something updates every frame, the quality of the BVH might not have to be too great, but I still want to have a kind of an optimized BVH for traversal. So I'm thinking about having, when you're in a region of a map, say this is we can call this like a chunk or a cluster of tiles. We'll have so let's just call it a chunk, because everyone knows what a Minecraft chunk is. You'll have a chunk of tiles loaded in at a time. So there'll be another chunk over here. And obviously the chunks that are on screen will animate, whereas the chunks that are off screen will not animate. And it means that we update a bunch of small BVHs which are kind of near don't have a lot of nodes. So those ones will be unoptimized, but the BVH, which is this thing, won't be optimized. Sorry, it will be optimized. So when you build it, like when we load the chunk in, we build that BVH, that mid-level BVH. So we can have like, let's go up here or something. So essentially, it will just break down into a tree, and then when it points to some leaf node, I'm just drawing a binary tree for some reason. Ours is a quad tree, but it's just to show the example. This leaf node here, it's kind of worked out to be balanced, but these leaf nodes here point to a tile, and we don't have to keep creating this tree every frame. We can have the majority of the tree, or at least the top of the tree, Yeah, so these will point to more BVHs, bottom level BVHs, which make up a tile. We can have the higher up the tree could be more optimized, such that we'll have less rays hit the same nodes, basically. And then obviously you'll have a top level BVH, which will be rebuilt every frame. And this one can reference these mid-level BVHs. So the top level BVH, again, will be another tree, and the leaf nodes will instead be, so these leaf nodes here, here, and here will just be different chunks, and these will get rebuilt every frame maybe. Or maybe not every frame, every time a new chunk needs to be loaded in. So I think that seems like a sensible setup to do. This is why I want to add support for mid-level BVHs. If you look at ray tracing APIs on the GPU, they don't really have those. And some developers say they would really like a mid-level BVH for probably similar reasons to what we just said. They want to be able to not have to rebuild massive amounts of things. Yeah, so the other option would be each tile is just, the whole idea of a tile goes away, and you just make one bottom level BVH, which is the chunk. Maybe that's the other approach we could take, since they could all be animating. But yeah, maybe. Yeah, so I guess I can think about this one a little bit more. And the other thing we want to do is also optimize the, or do another pass over the BVH node structure. And yeah. And then we also want to write like a build function, BVH build function. That's basically what we want to achieve before we do the top level stuff, I think. Or maybe this mid-level one is the same as the top level. So let's get started on this custom heap allocator. So it's CPU side. So I'm going to do it in the graphics, GFX, internal. Because it's not going to be publicly facing, but I always put my type definitions and full declarations in header files. So this will just be the BVH node allocator. So the way I'm thinking about doing it is I could have called it a heap allocator or whatever, but I think it's just better if we just say what it's specifically designed to allocate for. Just allocate BVH node indices, really. So because it's indices and not actual memory, we can't store the headers and footers in the memory because the data is on GPU. But yeah, the allocation is being controlled from the CPU. So we need to have other data structures to represent yeah, we need to node range allocator, I think, will be good. So BVH node I guess we could just call an allocation or something, or so you want so we need to probably have some form of free list or something of all the free nodes, and we probably need to have our free ranges. Or maybe we could I could just call it a variable range allocator maybe, and just move it away from being. Should I generalize it or make it specific? I think I'll just make it specific for now. So I need. So what information will we need to know when? Could call it allocator entry. These are very long names though. Range allocator entry. Doesn't make it any shorter. Cool. So I think what we would like to do is you kind of need to keep track of every allocation and every free block of memory. So we could probably say start and end of some kind, some range, end is exclusive. I think to defrag, you need to track connections between memory blocks allocated and free, and merge consecutive free blocks into one. Yeah. So I think for defragging, all I need to do is shuffle. Yeah. I need to see if there is a free block. Yeah, that's right. Yeah, I need the connections between all blocks. That's right. So the case is, one thing about doing for defragging is so this area is used, and these two are unused. I don't know if that's the wrong way around, but anyway, this is used. These two are unused. Then I just need to like move this back here, and then we've got a larger consecutive range. So the way I'm thinking about doing it is just having another buffer on the GPU, which is probably smaller, and it holds. This is the maximum size of a BVH that could be, and we basically just copy it into there, and then we then can copy it into here. So this will then solve. Well, we only do this if the memory can't be copied there without overlapping itself. Because if it overlaps itself, there's a problem. So that's how we'll solve the overlapping copies, I think. I think that should be alright. And then we don't have to store the same memory on the CPU as well. Because the other technique is you just basically have 2 copies of the memory and you just re-upload it again into the new place and get rid of the other one. But it should be quite easy to write a memcopy shader basically that does that. Yeah, we need like a BVH node range from start to end. And we need the ranges to be able to point to the next block, the block next to it and the block after it. So maybe just call that block. So you either have it all linked listed together, or you have it as one contiguous array, and then you shuffle everything along when you need to insert blocks. Then you can move blocks around. Don't think that you can move blocks around, but that makes sense. You don't need to preserve valid pointers. Oh yeah, I can move memory around because all my indices are relative. So in the BVH node, everything within that tree is relative from the base index. That's good. Hey Psycode, welcome back. Are you familiar with the 2-level segmented fit? Dynamic allocator? No. Oh. Really? Yeah, I've seen the offset allocator. I actually had a very similar idea to that one before, but with power of 2 buckets. And I'm sure tons of people had that same idea. And that custom allocator that he says solves it with the using floating point buckets, or the way that the floating point thing, the way floating point works, basically the bucket system works that way as well, where it uses a low precision floating point number. Yeah. I've not heard of this though. And if not, why isn't everyone using it? Wait, why am I signed in to Google? Get out of here. Dun-dun-dun. Currently assumes an architecture, that's not a problem for GPU. Everything's 4-byte aligned. I don't get it. I need pictures. Oh, is that what it does? It just uses the offset allocator is what it uses. Same algorithm. Right. So, how does it solve fragmentation? What's the bit that solves the fragmentation? Because you've got one block of memory. Fragmentation is just inherent problem of dynamically sized. Like, the fact that you can free a dynamically sized thing means that it inherently creates fragmentation. Whenever you free, it consolidates blocks beside it automatically. Yeah, that's just the nature of a heap allocator, isn't it? If not, you've just written a dumb allocator, right? Like, I don't understand. Like, if you've got an allocation here, and then you go, oh yeah, free this. Why would you leave it free but as two separate blocks? Or keep the three separate. Why would you not just join all those three blocks together? That's just inherent way to write an allocator, isn't it? Instead of regular right. You don't waste. It doesn't solve fragmentation. It just makes it less relevant. Because sizes are optimized on good fits. You don't waste as many blocks. And when it can, the free blocks will consolidate them properly. Right. I see. Yeah, so yeah, you basically optimize the allocation with it. Yeah. That makes it 01, but yeah, then you're not getting waste. Yeah. Yeah, and it's not searching for best fit as well. And then okay. Because you can search for best fit as well. Yeah, I don't think I'm going to bother doing anything hyper optimized like that yet. I can look into it later though. But yeah, it still doesn't solve the fragmentation problem. You inherently get fragmentation. But we always have a good defragger system anyway. Yeah, it makes sense though to do something like that. Yeah, I've done the power of two bucket stuff before in the past with the count leading zeros. It's a really good trick. I do like it a lot. So I'm thinking we should probably do pointers to next and previous blocks. Because, or at least indices to next and previous blocks. Why is that though? Or block previous index. Why do we need, I guess I'll call it ID, so 0 is null. Why do we need a next and a previous? Yeah, so we can free them, and we'll keep them as pointers or indices to so if we do the optimized search stuff, we can always add it on later. But for now, we'll just do a stupid one because it'd be quicker to add, I think. So we can just have our array of blocks that we can bump allocate from. Is that wise? Oh, I forget these things. Source core or engine core. Yeah, core define stack, you know. Core define stack. in a way, this IntelliSense is way better than the LSP one, because the LSP one will just mess up sometimes and you won't get it. But I guess if you define stuff in macros that's code gemmed, this one won't pick it up. So we can bump allocate those blocks. And then we'll probably have a free block. Evening Pete, how's it going? Pete Ricks. I used TLFS2 for my allocator, works well for me. I've never heard about it standardized in a name though. I don't get what makes it the TLFS thing. Is it because you bin stuff into buckets? Is that what makes it that TLFS? What does two segmented mean? You have two buckets essentially. Yeah, but the offset allocator isn't two segments, is it? Oh, I'd never realized it used it. Because I'm sure it's got like a... Give me a minute. He's got some... Is it in the bins, isn't it? No. Number of top bins, that's not it. Bin indices. Yeah, I don't get what makes it. Right, looks in this used bin. Two-tiered buckets. First tier for powers of 2. Second tier adds further memory sizing for extra fidelity. Further memory sizes. Oh, right. Yeah. Okay, so it is because of that then. Yeah. That's interesting. Yeah, I came up with that by myself. I never knew the name. But yeah, I'm yet to try that floating point trick though, where it does it size based on the floating points. That's cool. Yeah, it's one of the reasons why I fell in love with count leading zeros, because I could do that trick. And then you basically look up in the array and then search along the array for the one that fits. Yeah. I use it all the time. Like, especially like looking over bits as well. It's great. I'll count trailing zeros. You use count trailing most of the time, innit? Good. So we've got an array of blocks. So whenever we need a new block, we just bump allocate onto there. We then want to have... So I guess we could just do the power of 2 binning for now, because it's not difficult to do it, right? Yeah, we can change it out for that floating point 1. Power of 2. So we probably at minimum will have a certain number. I don't know, how many are we going to have? Are we going Power of 2 bins, maybe we can just... So 4 bits will get you 16. So if we go 4 to... What's the number? I think it's 16, isn't it? So... Yeah, 4 to 16, so we need 12. So we go from 4 to 16. Is that actually more than 12? No, it's 12 in it. So... Powers of 2 from 4 to 16, something like that. Yeah, so that'll get you to the start. And so this will be the free list. Free list power of 2 bins. So whenever you need to pick up a free index 3 block, you can just go into there. Something like that. So you want to next in physical space. You probably also want to have like a start, sort of like a block start ID and a block end ID. Like these are physically, like they're physically at the start of the block of memory, of the whole allocation, the whole buffer. So you can chain through them. So you want to be able to say like which ones are next to each other physically in memory, and then which ones are, and then you probably just want to also in a free list next ID, so you can just daisy chain through it. I think that's it. So just to quickly, so this block start ID will point, so this is our whole buffer that we're sub-allocating from. This block start ID will just point there, right at the start, to whatever the allocation of free block is. So this could be an allocation or a free block. This next ID is, this block will point to whatever this thing is here. So this is like a whole free allocation. It'll point to that. Basically, I might do index because it's always going to exist. Always going to exist. And obviously the end one is going to point to this block here because it's the last block that's allocated. Yeah, I think that's all we need. So yeah, we could just use this. So BVH node range allocator init, basically how many blocks, what's the block capacity. We also want to allocate what is that sort of max number of nodes. So I guess you just say nodes count, how many nodes you want to allocate. We also want to deallocate. You want to deallocate. We'll figure out the parameters in a second. We also want to probably have a way to defrag. Right, so if you're having a way to defrag, you want to say see, I found the element. So the element that you want to defrag is probably, well, no. So, yeah, so we can't hold pointers to blocks. If we hold pointers to blocks, it means that we get yeah, they would quickly whenever you run like a defrag operation, they would become invalidated. Which is bad. So I can't return. Oh no. Because the ones that get invalidated are the ones I want to defrag. So you can, on an alloc, return a pointer to the block. Yes. When you free, you just free the block you've allocated, right? That seems sensible. And then when you want to defrag it, now you want to search over all of your allocation, all of your BVH nodes, and you want to be like, well, the one that is neat. Yeah, you do end up using both. Constant time storage time for real-time systems. Yeah, I don't think I need to read a paper on it. But when was this figured out? In 2008? Well, obviously was not even programming then. Yeah, maybe there's some more insights into this. Maybe I should take a look into it. Wait, did I even say I'm live? Bum, 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 bum. Yes, I think we want to defrag a block. But you typically want to defrag a block which makes sense. So you scan over the BVH nodes. If you got free to the left and the right of you, then yeah, free block, then you should probably defrag. Yeah. So I guess you could just say defrag a block. And then when you're saying defrag, it's gonna, you've got the old range. Yeah, so you take note of the old range and it gives you back a new range. And then you have to do the mem copy on the GPU right away. And the problem is though it could leave the other one. Yes, the defrag has to happen first. And if it doesn't happen first, then there'll be issues, but it should be fine. So that's a good one. Defrag would just, yeah, that's good. I like that one. Look to the left and move it to the left. Right. Where's my music at? Do you want to show the diagram? Oh, sorry. Page 9. Two-tier binning. Right. Can be represented as a two-dimensional array. The first dimension splits 3 blocks into size ranges a power of 2 apart from each other. So the first level index refers to the 3 blocks of the sizes from one power of 2 to the next. The second splits each first level range linearly into number of ranges of an equal width. Of an equal width. Yeah, I think this might be where it differs to me. There's that second lookup table. I don't know if I had another lookup table. My mum was a free list. So maybe it is different. Of equal width, the number of subranges is 2 to the power of L. Should not exceed the number of bits of the underlying architecture, so that one web bitmap will be represented by the availability of the free blocks in all ranges. So you've got the yeah, that is the bit width. I don't understand the second lookup table, not gonna lie. Yeah, I was streaming for an hour. I set up the my NeoVim because it got busted. I had to look into that. I've been looking into writing a custom allocator. But this is one that's just I'm a bit confused by it. So the second dimension splits the first level range linearly into ranges of equal width. So based on the bit width. Maybe. So if your power of 2, right. I think I get an idea what's going on. But what happens if you have multiple sorry. Best fit without searching. I see, maybe. So, but yeah, then you're limiting yourself. Right. Yeah, I wonder how you stop. So one, you got the duplicate entry problem to solve, and 2, you have the issue of filling up that dimension. So how do you solve those problems? You just make it big enough. So I guess in mine I want to use 12 across one dimension. So it's just 12 multiplied by however many free how many free blocks I expect to have at most. But I guess you won't have that many. You still need to do a bit of a search though, right? If you index into an empty slot, is that possible? Yeah, I don't understand about that one. Nope, you just have to do some CLZ or DTZ magic and just check the 2 indices. Or with a mask, and you have it. Alright, that's interesting. So there's an implementation of it. Right. So there's the first bin. But where's the multi-level array then? I guess he just has it in a linear array. Top bins, leaf bins. Right. Yeah, so we just saw the implementation. That was just public. Yeah, so... so there's that just request size. Locate free. So I don't know if that's... Right, I wonder what that one does. So just the line rounds up. Yeah, so you want to make sure that it's at least big enough to it's the smallest block size. That's cool. Locate free. Let's have a gander. Right, so if you have a size, mapping search. Mapping insert. Yeah. Yeah, so you count the leading zeros. What's that? Is that what it is? It does look very... Count leading zeros-ish, but I'm not sure what it is. Yeah, there you go. Bit scan reverse. Okay. So if size is bigger than the smallest block size, then round it up, guess. Then mapping insert. More blocks in the first free list. So after design mapping search for suitable block. First search for the block in the list associated with the given. No block exists, search in the nearest first level list. Return the first block in the free list. There's that second index, that's the one. Which I didn't understand is that second one. I guess that's another sort of count leading zeros thing, isn't it? Yeah, so I'm interested in how it fills up that second array. Because the whole point of the power of two buckets thing is you over allocate a bit, isn't it? You round it up. And then you over allocate. Yeah, I might. Yeah. So everything within that bucket is going to be good for you, basically, and then this helps you find the best one. But then I wonder how it fills that array up with the right stuff. It probably does a for loop over it all, I imagine, and writes it in. Yeah, makes sense. Right. So I wonder what I want to do. I probably just want... I don't recall how buckets are filled, just seeing different strategies. It's been a while since I studied this, fair play. Yeah, it's not a bad idea. Not a bad idea. So for this one, I think... see, I don't know. I think I might... Yeah, I'll just do my free list approach, but I still do the power of 2 buckets, and I'll just pick the first one or something and take that. So yeah, I can optimize it later. So let's implement these functions now. Should be pretty simple. So I'll just put it at like the bottom or something. So to initialize it, we need we'll do our core stack init. We're going to initialize the... Oh, I need to actually take the allocator in, isn't it? Kind of missed that. The old allocator is a bit longer, isn't it? Just shorten it a bit. All right. So we need the allocator passed in for every one of these as well. Let's redo that. Ooh. Okay. So core stack initialize allocator blocks with blocks capacity. Like that. We need a custom allocator, I think. We haven't initialized an array here. Why is that? Well, let's see what it does in the engine GPU. Right, let's get the static allocator, and we'll just pass that one in. It's getting a bit used to getting this. This theme's a bit taking for me to get used to, but I need to fix my NeoVim setup. Off stream. Right. So we allocate those blocks, or allocate the stack here with these blocks, and I think we want to push the first block on. And this, we need to know if a block is free or not, isn't it? And we also want to be able to go from get a block ID from a block and the other way around. Block ID and then also get a block from a block. Or a block index and then get a block from a block index. Yes, I think we need these boys and girls as well. So we'll put those in there. So this one is obviously just return allocator blocks data block take. So we should really do a bit of a bounce check on this. So block index and you know, really it should be done with a you know, make sure that block is less than or equal to, sorry, that data is less than or equal to block, and block is less than or is less than data plus capacity. Like that. Block pointer is out of bounds. So we just return that index there like that. Then we also want to return a get. That'll just be a core stack get, I guess. Allocator blocks block index. There we go. Let's make that a bit easier to do. Let's change my sleep on this. Screen locking. Where's the energy saving stuff? Where's the dim screen? Right, it shouldn't dim the screen anymore on that one. That's good. Okay, so how do we allocate a block? Oh wait, we want to just quickly standardize on this here, right? So we don't know if something is a free block or an allocated block just by looking at the block itself. So we need one bit of information. So which one of these are we going to pick from for that? What do we? See, realistically, these can just be U16s. And this could be a group of 4. The number of nodes is always you always have 4 nodes next to each other in memory. So we could probably get away with, no, that's probably right. That's maximum number of nodes we want anyway. Yeah, and if these should all just be U16s then, because you can't have as many blocks as you can't have more blocks than the number of nodes that there are. Doesn't make any sense. Those all be U16s. Neat. That's alright. Good old U16s. Happy with that. Free next ID. Oh yeah. Oh yeah. Oh, for the free bit. Yeah, so the free bit you mean? Yeah, to know if it's a free block. Yeah, we could stick it on there. Is that the best one? Yeah, it doesn't really matter actually. It could be any of these. Yeah, that's a good idea. Because on one that point, the blocks, you can have less blocks than nodes. So yeah, these would be good. 15. And then 1 is free block. So then the other one will be 0 units an allocated block. Neat. So we've got that standardized now. Very good. Very good. So now we can set this up correctly. So block, let's get all these boys and girls in. So we also need to have something passed in, which is how many nodes. Is it U16 number? Ah, oh, crap. Is it? It's probably a U16 per BVH, not a U16 per. Hmm. Right. So thinking about it, our array is going to be bigger than U16, maybe. But the buffer stores all the nodes. But yeah. So we probably actually want to have U32 for start and end. No biggie. Nodes capacity, maximum number of nodes. So we'll just store that. But the maximum allocation is going to be in 16 bits. I think. Yeah. That'll be alright though. We might not need to store it in there specifically. Right, so previous block ID 0, so null, null. Null as well. Yes. 0. And then what else? Nodes capacity. Now, yeah, that's all right, I think. So we must assert the node's capacity is a multiple of 4. Sweet. So we got that block in there, but we also have to make sure that our allocator block start and end index. So we got a block index, what's the 0, isn't it? Block start and end index is 0 and end index will be 0. Okay. And then we need to initialize our free list parity buckets. So I guess we'll just chuck that in the. So we'll. See, I could have just memset the whole thing to be fair. Core 0 element allocator. So 0 the whole allocator. Initialize that. Core 0 block. These don't have to be set. Free list 15, the one at the end. 15, 11. Whatever that block index is. Allocator and block. There we go. I believe that strut layout bit fields are useless because of the padding. Ooh. What padding? Is there any padding? Strut layout. Because that's 4 bytes. Oh, it would be actually, isn't it? Yeah, it's been made useless now, isn't it? Because that's been... Damn it. Then there's extra padding here. Maybe, okay. Well. Yeah, we'll just do that. We got another U16. If we put another U16 in there, we can pack it. Maybe I'll just say U16. There we go. Take a note. Thank you, Clarissa. Appreciate it. So when we're allocating a certain number of nodes, it can't be above 64K though, which is great. It's good to know. So the problem is that power of 2. Yeah. Yeah. So we should be able to use so we need to use count leading zeros or something and find the highest set bit. So I think I've got that in my... Have I got that in my maths library? Definitely there for GPU. Layer page maths, types or something? No. Where is it in? Vector scalar probably. Yeah, so these things. I don't know if I implemented them for... I did. Yes, these the countering zeros or bits going forward and things. Cool, so I've implemented those. So that will give me the most set bit. The index of the most set bit. So if you take a number, I don't know what's going on with this count. Why do we update software? Why do we update software? It's just so annoying. Like, why am I typing into... It's like a calculator now, where I need to press enter or something on it. Come on. They've literally changed how the calculator works. So the result is here, and then you've got a non-result. You've got like an input box and then a result. It used to just be, this used to work on the input box, I think. I just used to type out numbers. Anyway, this is 1, 2, 3, so do the, what's the most set bit index? This will get us 7. Or yeah, bit 6. And then we'll add 1 to make it 7. So then we could say search bucket 7 or whatever. And that free list will contain free blocks where they always have a size which is larger than 128. So you over allocate by the nearest parity. So we'll change that in the future probably to that floating point 1 that the offset allocator uses, but yeah. So this will get us the most set bit index. We add 1. So this is the next power of 2. And then we've got to make sure that when we index into this is from 4 to 6. So if we take 4 away, so we clamp it between 4 and 6 and take 4 away. Next power of 2 equals clamp. Next power of 2 between 4 and 16. Sorry, I said 6 earlier, 16. And then when we index into that bucket, we just say free block free list ID or something like that. What did I call it? Yeah. Allocator, one of them. Next power of 2, take 4. And that should overflow. So this still has some issues, which we'll get into. So then if let's just write something really basic out first and we'll prove on the problems. So if it's null, return null. If we have 1, we'll just take the first one. So you can just call this allocator block index, or it's block free list ID take 1. So that gets you the index, and then you mutate the things and claim it. So you say is free equal false, and then you just return the block. Now this has a few problems, right? The first problem is we've just claimed the whole block. So we'll start with this one. But the other problem is what happens if that free list is empty, but the next free list is not empty. So we need to probably search up the free list from there and just grab a bigger sized one. Maybe you just keep going up until you reach the maximum do you just search all the bins? Maybe. Or would you populate the free list with things? Yeah, I think what we'll do is we'll pre-populate all of the free. Here's what we're gonna do. We're gonna we'll pre-populate all the free lists with the same value. Is that a good idea? No. It's probably a bad idea. No, maybe it's a good idea. So yeah. Free block or block free list ID, something like that. So we'll just go over all of those. We'll go from allocator, and we just populate all these things with block free list ID. The way it works in TOFS is that your free blocks span the entire buffer. And when you allocate, you subdivide the block and allocate a free block. Yep. For the remainder, and one block for the allocation. Yes. Yeah, exactly. Yeah, that's what we're going to be doing. That's cool. So the start, you have one free block. Yeah. Yeah, that's right. So here's our one which spans the whole thing. And I'm putting it in all of the power of 2 buckets. So we can just do one lookup. But the issue is we'll need to issue is you need to search it. We need to search it anyway, I think. You need to search over them anyway. No, because you just do the power of 2 lookup and set the 1. No, you wouldn't. Yeah, I'll just do the search later. There's a lot of things set aside. So I think we'll do the search here every time you allocate. Let's just try it this way, actually. So you don't need to do the search every time you allocate now, you just index into that. So I guess let's fix that issue. The next problem is so unless it's an exact fit, you Should I do a block size as well? So I probably want to do like a range count or something. So that gives me a number of nodes. For a given block. So that's just block take and take block start. Okay. So so unless, damn it, and then pluralize it. Okay, so if they're equal, any blockbusters? Oh, yeah, blockbusters don't exist no more. Actually, I think it still does. Like, it was the store where you went in and then never actually rented anything. Yeah, searching. Yeah, I want to try and avoid the search where possible, I think. Hopefully, we'll have to still search though if you're the first block in the array. So block nodes. So if it's exactly equal, you just return. After setting it to free block false. But if it's not exact, you allocate a new block. Metadata thing. And you call it free block. That'll just be a bump allocate core stack. See, when you yeah, we probably want another function which says like allocator. We should probably separate some of this functionality. But yeah, we want a way to say like alloc block, where it's just making us an empty block. Because I think we're going to need that core stack push. And it could maybe do some extra bits in there as well, I reckon. But for now, just return a stack push. So we allocate ourselves a new free block. Is it always free? Is it always free? Because when you delete, we'll just set it all up. Maybe we'll give it a bit of memset as well. But these are all the things we need to set. We'll figure out when we need to clean up the code if it's worth doing some stuff in that function. So at the start is going to be basically block block start plus nodes count. Where's my assertion where it's got to be a power of 4? Or a power of 4, a multiple of 4. This one's got to be a multiple of 4 as well, isn't it? I used to rent stuff at Blockbuster, actually more like Mom did. How's it going, Sockham? How's it been? Have you been up to much? Bit warm. How old am I? 29. I'm 30 in March. So the end is going to be block start end. And then the previous block ID is going to be whatever the block. Node range allocator block index. That'll be allocator block plus 1 from an index to an ID. And the next block ID is whatever block. Wait a minute. So if you're taking from a block, yeah, and then you're saying that you're stealing the one that this one was pointing to. Free list index. Well, you gotta insert that somewhere in the free list. Oh yeah, so you steal this one's free list index. Yeah, steal it from that block. So you've then got to change the stuff from block. So block the start stays the same. Block end changes. Block end has to be where free block start is. The previous block stays the same. The next block has to change. So that changes to whatever this free block is. Then the free list next ID is then zeroed because it's not a free block anymore. And then we return block. So that should be as simple as, oh yeah, and then you've got to insert this into the free list. So we probably want another function for that as well. So you've got to block this out of the, oh no, you've inserted into the free list. Ooh. So we could push it on the head. Although pushing on ahead will mean you have to scan more. Sorry, set it over the whole array. Fair play. Yeah. My wife's actually a bit older than me. She's, yeah. I won't say her age, she's much older than me. Yeah. Cool. I still think though we probably had a similar childhood though, because you probably grew up with bit more of the yeah, the technology didn't used to come out as frequently. Like I still got like a Game Boy, right? And you probably got a Game Boy as well. And I still played a Sega Mega Drive. So I'm guessing, do you play those? Yeah. So those what I grew up on those ones. The Mega Drive and the Game Boy. The Game Boy was good, man. And the Game Boy Color. I didn't get to play the original NES, no. We didn't really have Nintendo until Game Boy. My dad was a Sega guy. He liked Sega. He got the Sega, the portable console, whatever that one was called. The one that just had no battery life. Yeah, my dad had the Sega... I forgot what it's called. The Game Gear. Yeah, that one. PS1 is best console ever, prove me wrong. It's alright. Crash Team Racing was one of the best games on there for me. Crash Team Racing was just so good. And then Spyro the Dragon as well. That was fun. Spyro 3. Bit of Crash. Especially Crash 3, Crash 3 Warped. Good one. I don't know. I think PS1 trumps 64. So if I put it on the... Every time I try and put a block on the head, I have to scan over all the blocks and see their size. Yeah, I'm not doing this. This idea is dumb. So when we initialize, just put it in the last one. We'll do the scan every time you alloc. What are we doing? Where's the index? Oh, 0 in it. If free list ID break. Got a bit of a scan going on, but that's alright. It's already power of 2. Power of 2 minus 4. Boom. Yeah. But if it's still 0, then return not. Bingo. Right, so then we want to have another one where we say put free list on the head, basically, isn't it? Like add free list, add. Because we do that kind of often. Let's just write it in, because maybe we can combine all of this into one. But yeah, so free... So, allocator... You want to figure out, like... Power of 2, and then... free block. So we get the number of nodes. In free block. Add 1 to the power of 2. Clamp it. then you can insert it into the free list. There's a bit of an issue doing it like this. Right, so the issue with doing this is you're going to point to where the block was pointing to, and then you're going to get pointed to by the free list head. But the issue is what was in the free list head at that point is now messed up. So I think you need a free list previous index as well to patch. Yeah, so it can't be a singly linked list. It's got to be a each block needs a previous one as well, and this is where the extra U16 comes, so we don't have the useless padding anymore. Neat. So yeah, we'll do some patching of that free list. So the free list index doesn't get set, but we've still got to unlink it. So we unlink it if block, get it to point back to the previous. Free list next index or ID, tick one. Next free block, the previous free list previous is equal to the block's previous, free list previous, and then you clear this one to 0. Then if the I think that's right. And then if you have a previous free list entry, you get the previous block, and the previous block's next block is what your next block was. And then you clear that free list in previous back to 0. Yeah, so that's all good. So you don't set the free list thing, and then your well, you do set it, right? Your free block free list previous is nothing because you're going to be on the head, and then your next is going to be whatever was the head. Which is like that. And then you're going to become the new head. Like so. Sweet. So that's allocate. I think we should double check all that code for any bugs. But we could probably standardize some of this into a function somewhere. Tab indentation. Yeah, I removed the colors because Neovim broke on me. I much preferred my previous theme, but I can't. I updated my system and Neovim decided to break with all the plugins that I had. So I tried updating the plugins, didn't work. So I just did the quick thing so we could actually just get programming today. But yeah, I need to figure out how to where I want to go next from this. Because yeah, I might just get my Ascent theme back. Maybe, and I maybe need another plugin to just get some types to show up or something. I don't know. a bit annoying, to be fair. Don't know anything about Nano. The only thing I know is that you press Control X to get out of it. That's all I know. And it's basically like standard text editor in command prompt or terminal, which I don't really see the point in. Other than if you're on a server, I guess. SSH in it. I tried grayscale, can't get into it. I've been meaning. Yeah, it's really taken me a bit to. It does really. You know, I'm used to having a bit of eye candy, not just a little bit, right? Just a few colors, like literally like 3 different colors, and you know, one for the types, one for symbols, right? Like star and plus, and maybe another one for strings, like constants. And I think that's me set. Right, I don't need the rest of the eye candy. I don't need it like a rainbow editor setup. But I've yanked out all the colors now, and yeah, it's taken me a bit to, you know, like figure out what's what. Whereas I used to just be able to, my eyes used to know where to look better before we did this. Yeah, I've used to have it and it's gone. It just disappeared from my file system. I think it was like, how what it was? Or was it Ascent like you spelled it? Yeah, this is it. So we was using the red one because I was looking more for iceberg. If you remember me using iceberg, and I swore down by iceberg. Iceberg was a good theme, but this one we took this one and then I made it work more with tree sitter by taking the things and applying it more everywhere. Maybe we'll get this one back in. Yeah, this is what we're talking about. Let's get this one in here. I couldn't find it earlier for some reason. I found something else. Overwrite that one. That was a trash one. Color scheme. Ascent. It's a bit better. But I want the red one. Ascent color. I'll set ascent color. Color. Hey, this person's in English. Like me. Oh, G. Global, I guess. I don't even know anymore. How do we do this? It's probably on the GitHub. Or is it pronounced GitHub? Bump bump. Oh, let. Oh, bit of let. Then I reapply the theme. Ugh. Yeah. I don't know. Yeah, then I set a darker color for the background. And then I made it apply everywhere else, like for constants and stuff, and types, using tree sitter. Let's get this one back at least. I'm all for that. In it. Where's the color scheme? Accent color red. Right, let's see how that works. Oh yeah, we're back, kinda. Right, this is better. We've got... It's still not amazing, but at least constant show up as different colors. Anyways, figure out how we're gonna get back into things. Kind of just got a splash of color now. Right, type function calls variables, yeah. Yeah, it gets a bit too much though when you start differentiating everything. For me at least. Yeah, I mean accent. I guess it is pronounced accent, isn't it? Yes. English. It's my first language. You should, yeah. You know, go easy on me. But yeah, you can change it with different colors, I guess. But yeah, I took this one and I made it. Because what I was looking for is a replacement for iceberg. And yeah. See, I want this just with a little bit more, you know. I guess it's putting white on the types and stuff, but how are they getting that on the types? Because I'm not getting that. So I guess they've got like support for something in there, basically, but I'm not sure what it is, right? Oh, they've got the FNV hash. I don't know why they got that in there. For a theme? Yeah, how are they doing... Right, here we go. So whatever is an identifier, if you... I don't know how you get that to work. Oh well. I'll figure that out in the future. Back to programming. Yeah, iceberg. But yeah, the only complaint is just a bit blue, and sometimes you just want something a bit different. You know, I've had this one for so long. Maybe it's time we change. But I can always just change it to green as well. Right, so let's double check this one. So we allocate, it has to be multiple of 4. Most significant bit plus 1, next power of 2, clamp between 4 and 16. And because it's an index, you need to take 1. Actually. Because you're going to overflow that array of 12 elements. So you don't need the plus 1. So you don't really get next power of 2. You're saying, what power of 2 am I? Is that right? So if you got bit 6 set, you're going to go into index 6, which would be the next. Bum, ba, bum, bum, ba, bum, bum. Yeah, so say if you have something like that, you want to make sure that you look in the bucket which has let's just start with the lowest. The lowest we want is bit 4. Yeah, so that's going to be the first bucket. So if you've got 16 elements or more, um, yeah, well, 16 to like 32 in it. So yeah, if you've got less than that, if you have less than that, you have like these bits down here. You get your most set bit, that'll be 3. Then you add 1, go to 4. I guess it's still correct. Yeah. Yup. Okay. Climb it between 4 and 16. Yeah, so 4 will get taken away to 0. Yep, that's fine. That'll loop over in that array and go up to 12. Oh yeah, sorry, the maximum value this will reach is 11. Okay, that's good. So that won't overflow there. If we find a block break, if the block index is 0, return not. What is blocks for, by the way? So we're doing a kind of like a free list allocator. So you allocate a range of nodes, and we're just calling that a block. So essentially you have a buffer on the GPU where all the BVH nodes go. We want to allocate a portion of memory for our BVH. So we're just making it such, and this is called a block, and then this will be called a block as well. This is now used, and this is now free, but they're still both blocks. And then you can free this block back, and then it'll just go back to one block like that, right? And this one block covers the whole range of the buffer. Yep. Yeah, so all the blocks are different sizes because it's a range, and the ranges can be different. Is a big fan of dark green background? Agree with that. Sounds pretty old school, to be fair. Like, you know, green themes. You know. Maybe we should get cool that cool terminal. You know, the old school terminal, cool retro term, as it's called, with the whole CRT rendering going on. Whip that bad boy out. Right, so we take that FreeList block ID, take 1, make an index, get the block out. It's no longer a free index if there's no next item in the free list. We unlink it. We did check this already, but let's just double check. So make the next free block point back to where the block that we're taking, where it's pointing back to. Then if there's a previous one in the free list that our block was pointing to, take the previous free block and make it point to where our next block was pointing to. That looks all right. We clear out the next and previous free list indexes in our blocks that were just allocated. So I guess you'd want to say unlink free list. We may or may not need that in a function, we'll find out. I guess I could comment this as well. Find the nearest. Okay. So take the nodes count and find the next power of 2. Then search from that bucket until we find from that power of 2 bucket, until we find a free node, a free block. Right, and we just take the first block. We forgot to update this, isn't it? So there will be no free block previous because it's ahead of the list. So yeah, that was pretty dumb. So the block will always have a next. So we added the previous because yeah. I don't know why we're still going to need a previous index though for defrag, I think. Wait, are we? Yeah, I think we still need it for defrag. Yeah, so unlock it from the free list. So it won't have a previous. But we will need to make sure that we store in there. I guess we'll call it bucket. So we can know how to mutate after. So you need to say bucket index is equal to whatever the next free list item is. So unlink block from free list and make the next item the free list head. Yeah. Cool. We should probably assert that the next, if it has a next, we should also, wait, what is this? If it has a next, then the free list, the next block has no previous anymore. Cool. All right. We should probably assert that block previous free list previous index equals 0. Block is the free list head that has a previous for some reason. Oh no. I think you need to find more beer. But that requires going to the shop. No. Rightio, I think that's looking better. So we unlink it, store it back in the, store the next one in the free list head or clear it out. Get the number of blocks, so a number of nodes in this block, if it's exactly equal, and we should assert that it's if so if the number of yes, the number of nodes in the block has to be greater than or equal to the number of nodes we have requested. Wait, it probably never is equal, because you're always looking at the next power of 2. Always. You could probably do a bit of a trick where you say if it is equal to the power of 2, maybe, but because that is also true, right? If it's the power of 2, you probably want to take 1. It doesn't matter. We'll leave it in, because we probably want to change it later anyway to a different, slightly different approach. Block nodes count. Yeah, so I want to say like block is expected to always have more nodes than requested. Block has this many nodes, and we have and this many nodes was requested. So we say block nodes and then nodes. Cool. That's all right. It was a bit long, right? So we should probably drop it down to a new line. Okay, so that probably would never fire, but we'll keep it in there anyway. Because when we change it, it will probably fire still. Right, so here we are. Getting the number of nodes in the free block and trying to insert that into the I should probably make a function which just gets a bucket index or whatever, you know? Bucket index from, because this next power of 2 thing, it's not really used. So to make sure there's less clutter in the, you know, less chances of me reusing the same variable name and messing things up, or using the wrong variable name and messing things up, we should probably just have a thing where we say we want to get a bucket index or whatever. So you simply just need to pass in a number of nodes, and then you can just get that quite easily. So it's just this code here, right? Power of 2, and then return power of 2, take 4. So that's nice and isolated now. So we should just be able to do nodes count there and get rid of all that silliness. And then we'll reuse that bucket index variable. Actually, we'll put the free block in there now. So figuring out where to insert that back in. So free block is, we allocate a block. Maybe this same function call can actually be used in the initialize function here. Free block start is start plus nodes count, and end is equal to the block end. So yeah, the new block that we've allocated just allocates enough, and then the remainder is in this new free block. We point back to the previous physical block in the buffer is the block that we've just allocated, and the next physical block is the one where the block was pointing to. Yes. That's all good. You see, I haven't updated the ones in the allocator itself as well, the start and end physical block IDs. But we shall remember that. Free list, previous index 0 is correct. So you've made that one the new head. Do we even need this anymore? Because I've done this here, isn't it? So you're the head, so we just point. And then we store ourselves in here. So that's power, whoops. Wait, this is the free block. So we could go into a different bucket. So yeah, wherever this one is going. You can go into a different bucket. Yep, is free block true? That's fine. So we need to make sure that the next, where we're inserting, we need to make sure that we get this next free block ID. And then make sure we patch it to point back to us. So you say, it's basically like this code here. If there is a next free block ID, what we'd like to do is get it out and make it point back to us. So this would be our free block ID. Where is that? There's too many of these being used. Free block ID. Right, so that's free block ID. Oh no, this is free block ID. Right, so link free block into the free list. Or make free block the free list head for this bucket. And make the previous head point back to us. Point back to this new free block. Yeah. So free block ID. Yep, the bucket index is good. Make a point back. What is, yeah, this is bad. This shouldn't be here. So your free list next, you've already set that up there. You've not got that there. Okay, that's good. Yep. And then put it back in the free list, or put in the free list head. Cool. Right, so then you're patching the block. Now we patch, remove or shrink the block. Why is it saying free list next equal? Yeah, I shouldn't do that. Okay. And then block next ID is this new physical block here. Yes. Right, so that's one more thing we forgot, is that the if you take a look at the allocator, it retains the block start and end. So this is for the whole memory range. We could also know where they start and end. Might be useful information to know. Maybe we can debug, visualize it or something. If we want to in the future, I don't know. We'll find out. So allocator. So if this new block is at the end, yes, if block next ID is equal to 0, or if it was equal to 0, then well, no, because you've changed it, isn't it? You're changing it there. Yeah, we should already look at free block. Oh no, it's fine. Yeah, so then this would mean allocator next or blocks end index is equal to whatever that free block ID is. And there we go. Oh, that should be it. Hey there, Castel, how's it going? How are you? Welcome to the stream. So I'm pretty sure that's it. That's a bit of work, but that seems to be solving all the problems now. Right, so let's take the... Let's do the deallocate. And then we'll do the defrag as well. And I guess we can write some usage code up and test it out. Make sure it works probably is a good idea. Because we don't want to allocate something wrong on the GPU and then give some indices out and it just burns the whole place down. So we should be careful. Right. I'm just going to grab a quick drink and then we'll come back, write the dealloc function, which deallocates a block and returns it back to the allocator. Right. BRB. Ah, my wife cooked up some pork belly. I was going to be having this for the roast today, but you got a bit lazy. Well, I actually ran out of veg. So went and got some Subway instead. And this is part of the reason why I'm so tired. It's because I had so much Coke today. I'm just crashing hard. I need to stop drinking Coke. It's bad. It makes me more tired. I think that's what it all does now. Yeah, pork belly's good. You know, you need to make sure you sear the fat. You know, even though you just got like, you know, it's the same with bacon, right? You want crispy bacon. When people say they're not a fan of bacon, I think it's because they're not cooking the fat enough. You know, you got to get that nice. You'll make it nice and crispy, you know? Alright. That's so good. And this pork belly, season it. Yeah, a bit of that paprika. Mmm. Good. But Yeah, Coke. I need to quit Coke. Because I think the other night, Thursday, was it? It's Sunday, right? Thursday when I came on, I hadn't had Coke Monday, Tuesday, Wednesday, and Thursday. So when I streamed on Thursday, I had so much energy. And it was just fine. Today I just feel like I can't even piece sentences together. Too much Coke. Need to quit. I think the thing is with Coke as well is it's a lie. It makes you more tired. Pure lie. It's probably a relaxing drink. You know, on a nice warm day, yeah, a nice cool Coke, and you drink it, and it makes you happy. Yeah, it's a good idea. Especially ones with sugar in it as well. Like, it has like 13 grams of sugar. Right? And that's half of your allowance, and you're just drinking it. Like, what? Bananas. Bananas. Alright. Make sure I got that pork belly juice off my fingers. Alright, we're good. Put it all over the keyboard, you know. Like not stopped as in I won't drink no matter what, but I just don't feel like drinking anymore. Yeah, good idea. And to your IPA beers. Yeah, I'm not. IPA is not so bad. I think. Yeah, some of them are not that bad. It's just not my preferred drink. If I'm gonna drink and drink a lot, rum, and whiskey. No, just mostly rum. Yeah, especially Kraken. If you have Kraken rum, that's a good rum. You gotta have. I don't even spell it. There we go. English. One of these. It's like dark spiced rum, you know? A dark rum goodness, but with a spice rum goodness. That's only when I drink. I don't really fancy drinking. Unless we're all drinking. So the thing is, Ket Pain, you're experiencing the pain of upgrading your system and then opening up NeoVim when you're just about to stream and realizing, crap, it's all broken. So I've had to delete all the plugins, which has been quite good because the IntelliSense is now not so bad. Because the IntelliSense was kind of crap with the language server protocol sometimes. It's just fall back to simple string lists of strings. But I've also lost all my syntax tree setter highlighting, which I used to have. It was worse. And drink on weekends. I used to do that mostly as well. Yeah, I didn't. When I used to go out most weekends, but I'm now a married man. No need to go out anymore. What's the BVH? A bounding volume hierarchy. I was going to try and make a joke, but my brain was like, nope. So essentially you have a tree of nodes, and the leaf nodes are the primitives that you're trying to draw, and all the parent nodes wrap around the child nodes, and you have bounding boxes around everything. So if you have like, I don't know. But yeah, search on Google and you know exactly what I mean. Images. Allocator, dealloc. So we've got a block. We should probably make sure. Yeah, we want to get the block index from the block. How's it going, Ket Pain? What have you been up to? Look at that. IntelliSense. Not, yeah, no LSP, just strings. Way better. But there are some nice cases where it does help. Sometimes the context is not enough that the LSP provides and it just messes things up. Yeah, what am I doing? I am putting the block. Neat. And then that will serve as a problem. So no need to put assertions anywhere. So the idea is we want to basically so we need to unlink it. From the free... No, we need to link it into a free list. Wait, we push it on the... So now it becomes a free block, and then we push it on... Interesting. Is it basically this code? If so, we can just put it into a function, I guess. Next free block. No. Right, it's just this. Right, no function. It's not the same. So we get the bucket. Hang on a minute. Oh, it's kind of the same. Oh well. And you need to then look. We need to try and join things as well. A bit of joining, so yeah. But let's just do the simple one first, and then we'll make it better. So we get the block index, we get the bucket. So the number of nodes, get the bucket index, get the next free block, if there is a next free block, get the next free block itself, and make sure that it points back to us. Then we are now the new free list head. Ta-da! But what happens if physically when you so this is all we need to solve, right? If you this is the thing you're freeing, it's the used node. Or the block, right? You got a free block here and a free block there because this one points back to this one and this one points forward to that one. So when you free it, you need to check the previous and the next. If they exist and they're free, you join with them. And so if the left one is just free, you join that one and you don't bother. Yeah, and you get rid of yourself. If... Oh, I didn't think about that. Yeah, there's something we need to handle. We'll get to that in a sec. And if we point... Or if we point forward, right, we become the start of this one and then get rid of this block. If they're both, we need to get rid of these two blocks and make this one as big as that. So there's just one block. That's the logic we need to do. Oh yeah, acceleration structure, words, that's it. Not much, just playing some games with my buddies. Awesome. Or I was, okay. Neat, what game was you playing? Right, so this is where we... So if the free block still exists... Oh, so if this block still exists, then you add it on to the... Okay, so that's only if it doesn't join. So this is where we need to do some joining questions. So we say if you have a free block to the left, so I guess you just have a boolean, is free block left. Screw it. Let's make it read like English. Is left a free block? Block you know what? No. No English. Is free block previous? Is previous a free block? Okay. Block previous ID and we need to do a get on the block is free block. Block previous ID. Neat. Previous. Next, and voila. Right. So now we do a bit of logic where we want to say, well, if they're both set, if the left is set or if the right is set. So it's very different. So if you have left and right, or sorry, previous and next is the terminologies. And then else, if there's just a previous, if there's just a right. Now there is going to be a bit of shared logic between the two, but I cannot be bothered to, there's a bit of shared logic between two of the if statements, but it's just not worth it. So I'm not going to bother with that one. And the else statement is going to be basically what we've come up with here. Where we insert it into, so there's no free block to the left or to the right, so we're not going to bother do the joining here. Oh, yeah, we can't join it with a free block, right? So no free block physically to before or after this block. We are freeing or deallocating. So just add it to the free list. Head of the free list. And make the old head point back to the new head. There we go. Yeah, neat. Oh, we didn't set the, if there is one in the list, make sure that block free list next ID is equal to this, right? Cool. Right, I think that's perfect as it is. So we pull it out, make the point back, and we point back to it, and store ourselves in there. Neat. Cool. So let's do if the next one is a free block. So if the next one is a free block, oh, we're still going to go in, we're still going to run this actually, isn't it? We're still going to run that code. Yeah, so the only time we want to run that code is if the previous isn't a free block. Yeah. So then, right, that's good. Physically before of this block we are deallocating. So add it to the head of the free list. Okay, so we're going to join. So if there's a next free block but no previous free block, we're going to go ahead and add we are going to extend ours. So we refetch that again. And then we're going to add ourselves to this next free block. Wait. So block end is equal to next free block end. And then the start stays the same. So this also this free block needs to be kind of removed from it needs to be unlinked everywhere. So it could be in the middle. So I think we need like an unlink function. Block unlink. Maybe you just need a block dealloc block, to be honest. We'll sort these out in a bit proper. So it needs to be unlinked, and then somehow it needs to get rid of it as well. We'll figure that one out. Block alloc. Yeah, so the unlinking code, basically something like this. If block free list next. We do the same old thing here, where we make the next point back to what our previous is. So previous is block free list. Wait, it's only if it's the free block though, isn't it? And then next and then if there's a previous block, make it point back to our block, or to the block we was pointing to next in the free list. What else? Any other kind of logic? Nothing physically. Well, there's the physical links as well, which kind of work in a very similar way. Yeah, maybe we should do that in here as well. So free list would now just be block previous and block next. So does that as well. Heard Biden drop how the president race. I never hear it all. I know, I follow it, but I don't really sort of discuss too many politics on stuff because people like to get really... Basically, it's always a negative if you cover politics these days because people are so fiery about it. Like, people don't have a discussion about things in a very unheated, in a very, people like to chuck around words like evil. Are these people evil because they believe this or whatever? And then they don't really want to have a proper conversation about it. So it just makes you look like you belong to one side, and therefore it limits you to 50% of the audience. So politics kind of sucks to discuss in most places. But I didn't realize Biden dropped out. Did he drop out by his own accord because Joe Biden was wanting to stay in the race? But right, he dropped out, and this is where you can do all the conspiracy theories, right? Where did he drop out, or did they, did they tell him to drop out? But to be fair, he's old, so like, why don't you just spend time with your grandchildren and why do you have to run the world? Yeah. They've got to find somebody to beat Trump now, haven't they? Pretty hard stuff to do that at the moment, but maybe possible. But yeah, I don't really like discussing politics too much for those reasons. Like we just had an election over here. Oh, it's just come up on my phone. Funny. Yeah, we just had an election here, and just it was crazy how many people were calling other people evil and all sorts. And yeah, I just wanted to have a discussion with somebody about the voting system, and they would just like instantly just go to the whole sort of politics of, oh, these people are complete evils, so it's good they're not in. Okay. Oh, sorry. Something. Politics is a tough topic. Like just like religion touches nerves. Yeah. Yeah. At least argue about Rust. Rust or C. That's kind of a bit of politics too, but like, yeah, it's nowhere near as bad because obviously it doesn't really affect actual people's lives in big ways. Because if you're a programmer, you know, you find a job where you want to, what language you can put up with, program in that, and then, you know, it's your choice to pick whatever language you want from there, isn't it? Really. So, yeah, I miss the old days where things were just a lot more, less heated. Guess we can blame the media for that and social media as well. Well, yeah, companies' choices, yeah. All right, so I think we can just call this dialog block, and then all the magic happens. It will link it. Yeah, we'll do all the unlinking from everywhere and joining and all that, which is pretty neat. So if you have a next free block, we are going to consume you. So let's just double check that all makes sense. If the next block is a free block physically next to us in the array, we're going to go ahead and take it out. Our node end index is equal to the next free block end index, right? Then we deallocate it. That's going to do the free list unlinking, and then do all the unlinking between the next and previous physical blocks as well. So that will solve all the problems we need, I think. Oh yeah, I need to actually get rid of the nodes somehow. I've not thought about this problem because we've just got an array of blocks that we bump allocate when we need a new one. But I think we actually need a See, we've already got the word free, but free is like, as in terms of like allocated, it's free. But then you've got probably unused blocks, which is going to be a different thing altogether. Unused block ID. Free list block ID, unused list block ID. So these are the blocks that are not used in the allocator at all, that we've bump allocated from this array. It's confusing. But yeah, so these are just free indices within this array, which are not actually representing a range of things at all. So we'll probably zero this thing. Yeah, maybe we zero it when we bring it back out. I think it's always a sensible idea, maybe. No, I don't know. So we get the block ID. And we add it to the list. So we make block next free block index. Or I could call it next block index. I don't know. ID rather. Is equal to whatever the allocator unused. And then this will be equal to that. Yeah, so we just add it to the unused. Right, add the block to the unused list. Since we can't just... Right, and then here, we say if there is an unused block, return that one. If allocator unused block, then we return, well, we get it. Allocate unused block, fetch, overwrite, we'll do a get. Get on the current block. And then we remove, then block, next block ID, that's the new head of this one. And then we return block ID, or return block. Yeah, so then that's the recycling. Music is still going, yay. Yeah. Yeah, I put that one in there because I think there was a period of time when there was tons of like people arguing about programming languages like Rust and Zig, and then someone comes along, you know, and then there's just everyone arguing about programming languages. So I think I just put it into that one with that robot basically. But yeah, I'm not against people talking about programming languages, but just when it's just arguing about them every single week, it just got a bit annoying. So I just put something in there to sort of, you know, get people out of discussing it too much and talk about programming, some other programming things at least. Not a big fan of Rust. Yeah, I programmed in Rust from 0.8 to 0.8 to 1.34, so for about 4 years. And I can tell you, like, if you're someone coming down from a, you know, okay, one, it's a nice sort of newer language. I don't agree with how they've extended it so much over the time, and I don't agree with how the standard library was standardized so early. But putting those things aside, I think if it's someone who's coming down from a higher level language, I think it's a good place to kind of just go in, because it's kind of, they got the new sort of features, and then they can also, the Rust is open source, so they can look at the source code of the standard library and start making their own stuff, and you know, but they have to do those things, I think, explicitly, which people just kind of get too used to the package manager and they don't do that. And I think it is a good stepping stone, providing people take the steps on the stones, you know. I feel like generally languages are like keyboards. Some are more sleek and or whatever, but won't really make anything better. It comes down to the user. Well, yeah, I guess keyboards are also personal preference. To follow that analogy, they're also a personal preference, and you might, you know, also for it to be comfortable for you to type on it all day, it might need for you to, you know, be a certain way. It's a step up from higher level languages. That's hard to argue. It's hard to argue, but still prefer C. Yeah, definitely. So that's the reason why I switched back to C, because I went C++, C, Rust, back to C. You know, because I was definitely one of those people who was thinking, oh, you know, you need generics, you need this, but then I realized you only really need generics for collections. Anything else, you don't really need generics or templates. And you know, the unsafe, I was unsafe in everywhere like a champ, and ultimately the borrow checker was just getting in the way, and it forced you to restructure things. And you know, unsafe pointers in Rust, they don't really want you to use those. They want you to use references for reasons, right? Because references kind of have many things good about them in Rust, right? They're can you have one, you know, it's kind of like a restricted pointer, isn't it, at the same time? It's got that going for it. I remember quite a few months ago what good options for C++ debugging on Linux were. Graphical, yeah. Yeah, there's GF at least. That's what we use, or I use. But let's just say we use it. Next, that's it. So it's basically a front end to GDB. Oh. Yeah, it's all right. It's better than using GDB in the terminal, but you still need to know some of the terminal commands. It's lightweight, installs in seconds, installs in milliseconds, and you know, it's great. Highly recommend. But state of debuggers could be better. They could be better everywhere, but we are stuck with these for now. There is there's probably going to be the one from eventually from Rad Game Tools, right? Rad Debugger. You know, it's made by Mr. Fleury basically and other folks. And there's going to be a Linux version at some point. But yeah, apparently it's improving making sure it's kind of as bug free as possible. I think that's what he was saying. And then it's going to port it to Linux after that. So that'll be cool. This will probably be what we end up using afterwards. I said we again, but yeah, just me. I'm sure tons of other people will do it as well. Oh yeah, you can obviously use the extensions in VS Code if you want to do that. That's probably quite nice. But obviously you have to build VS Code, and you might not like that, but personal preference stuff again. Generics for containers is nice, but at the same time you end up overgeneralizing things and creating nasty bugs. Yeah. The worst one for me is like when people go all in on C++, they make generic containers and they end up having to call constructors because types are not pod, and doing it all in there and templating it and all that. And it's just, you can make just like, here we go. So here's my dynamic array. I call it a stack because you push and pop on it, right? But you can insert in it too. But yeah, all of these are void. They work on the void stack, but the typed version, which is type def, and I just cast the pointer, just calls into the same function for all types. And they probably get inlined anyway because they're so small. But yeah, it's just a bunch of assertions in here as well, just making sure things are right. And a little bit of code. So inserting is just basically incrementing some numbers and mem moving, but pushing is just incrementing some numbers and returning the pointer, right? That's it. No more, no constructors, no crap like that. Amazing. I wouldn't mind a C++ equivalent with classes and member functions, but no RAII nonsense. Yeah, the things about the methods though is methods, it makes the code harder to read. You don't know where the function is defined. You can't do simple string search for it. Sure, it can be built. You can have some IntelliSense and press F12 and jump to the definition or whatever. But I find that the one in Visual Studio, what happens is someone decides to, call a function. So they've got this sort of like instance of a class, and they say init. But the problem is so many other people made an init method. And then you press F12 and Visual Studio in 2024 still can't find which init you're talking about. And it will open like all 700 of them and you're just like, damn it. In a box. And I guess you can use Clang and it's probably better, but still. This is why I wanted UFCS in C++. What is UFCS? Yeah, UFC. What is that? Uniform function call syntax. To be called using a syntax for a method. Oh, I think Odin does this. Right? Does Odin do this? Where you have like... Yeah. Odin does it with like the arrow operator. Yeah, Rust solves half the problem, but you have to use the colons, isn't it? The double colons, yeah. Yeah, but the problem is with Rust, you have to declare it all in the... Oh no, because you can have multiple imports, isn't it? Yeah, sorry. Answer my own question. Right, I see. This is actually one of the reasons why I moved from C++ to Rust. Because other things like enum match kept me, yeah. Cool. Yeah. Yeah. Yeah, that makes sense. Yeah, the trait stuff is quite cool. I like that too, because it's like a static trait and there's a dynamic trait. So you can choose the vtable if you want, or you can use it as the static guard on the static guard on the template arg. Quite cool. But when you program in C, you basically never use virtual tables anyway. Like you just use a bunch of function pointers if you need that stuff. So you basically But you barely use it. Because that's actually the best to just have plain functions. Yeah. Yeah. The only problem about the traits thing is you can't do the C++ way of templates where it's just like, trust me, this will work. So, you know, and then when you instantiate the template in C++, it will tell you, oh, there's a problem in a very unreadable way. But you can't get that in Rust, unfortunately, from what I know, unless they've changed it. VTails function pointers, similar solutions hurt me a bit, but I've grown to understand that you actually need them in specific cases, right? Yeah, I don't know. Maybe like the file, like a file API, maybe. Oh, sorry, like an IO one, I mean. But where it can read from a file or read from memory. But these days, I don't really need that because I'll just read the whole file into memory anyway, then do a memory reader. So I don't really need that. And then if you read it over the network, do the same thing, just read the whole thing from the network and put it into memory, typically. And the only other time I use interfaces, I guess, is different backends, or like GPU backends or something. But I think I've not done that with this one. I've just hard coded it in at compile time with function names. So my engine, for now at least, because I don't know if we'll need it, is we've just got a backend.h and then we just compile in the backend that we want. And we're only doing Vulkan right now, but if I needed to do another one, I'll just implement these functions instead. Right. Oh yeah, function pointers. Yeah, sometimes you need a callback. Yeah, I prefer to avoid callbacks where possible, but sometimes the callback is just simple. It's just got to be called like once or something like that, or in one place. It could probably be in a loop. I don't know. Yeah, Russ, I did find it a bit annoying having the micromanagement manage traits and such, but it reined in my over abstraction tendencies, and they're right. That makes the whole program refactors easier. Right. Okay. Yeah, I haven't heard that take before. It's interesting. Um, yeah, so we did that. That's pretty neat. Right, so if you have a previous block, I think you're looking at the end of the day at freeing this block here. That's safe. But you want to make sure, so you get the previous block. Yep. So you have the previous block, and you want to make sure the previous end is equal to the block end. And you get rid of that. And then if you're surrounded by, if you have a free block before you and after you, you get the previous free block and the next free block, and you make the previous free block point to the next free block's end. Then you destroy both the block and the next free block, and those will get unlinked. I think that's the logic, right? Yeah, because you take them from the free lists. I didn't handle this. If you're a free list head, we didn't handle those cases either, damn it. Right, so where's the block ID? So if the block ID, if block, sorry, what's it called? Allocator block start index. If that is equal to block ID take 1, then wait a minute, we're doing all this silly unlinking stuff. Hmm. Right. We'll come back to that one. So the free list, if you have free list next and previous, you need to wait, free list, if you don't have a free list previous, just an else in it. You need to look at the, you'll get your bucket. Get your bucket. So get the number of free nodes, get the bucket index. And I guess we'll do an assertion. Assert that the bucket index for allocator, forget this name now, block free list power 2. I could really call it buckets now, but anyway, bucket index. Make sure that is equal to block ID. Expected block ID to be a free list head. Be the free list head. Right, and then it isn't. But yeah, it is. So we store in there whatever block next free index is. Next free list. Free list next index is. Right. Neat. So this one here, physically, if you've removed it and you're at the start or the end. Yeah, I think we need to put that in there. So if allocator block start index is equal to block take 1, then we make that so you shouldn't be able to just destroy all of them. They should always be safe. Yeah, you should never be able to destroy one which is at the end. Yeah, you should never be able to deallocate a block at the end. We should not be destroying or deallocating blocks at the end of the heap, I guess we'll call it. Something like that. Neat. So yeah, we're at the start, move it on, block next, the physical next one, end. So end index is wait. Yeah, that's fine. Yeah, so that should when we destroy, should patch those. It should patch everything correctly. Right, so I think that's what a deallocate would look like. That'd be pretty cool. So defrag, let's quickly do that and then we'll write some test code. And we'll test this all out. So what is defrag doing? So you want to move. So we'll go over all our nodes, check if they're like a free block or something, and we've got to make sure that the previous one is a free block. I think that's the idea. You can only defrag one when the previous is a free block. So we assert can only defrag a block when the previous is a free block. Nice. So the basic idea is that you get rid of yourself and return the previous block. So it's a bit like this one here, right? Is previous a free block? It's exactly this, where we get the previous block, make the previous one consume us, and then we so maybe I should call this function remove previous block, but also removed. No. Deallocate the current block and return previous. Now it's not free block. So this one will now be allocated. So you got to unlink it as well. We've got to unlink the free list things. We should probably make that a function, not gonna lie. Where have we done it? Well, I don't know. It's quite easy just to copy the code around, to be fair, and specialize it. See, the previous one is free, is a free block, but then it becomes the new block. And then we'll set block to free block. And then return block. But we also want to say block is free equal false. No longer free anymore. Is that what we need to do? Yeah. So then the system can then do the defrag on the GPU and move it. Neat. That'd be pretty cool. Right, so let's get this thing initialized, or compiled first, then initialized. Right, it's saying that this one is probably different from the cool. Allocator. Right, what is this one talking about? Free block. Crap. Have we not got the free block yet? Oh, it's here. No. Okay. So if you see the number of nodes, if the next free block ID get the next free block, and then free block points to next free block. Cool. Right, that worked. Ooh. Next block ID and what? Excuse me. Block next ID. Whoops. Right, nearly there. Deallocate block. Well, we need the allocator in there as well. Whoops. Now we're there, we're compiling, so it's guaranteed to 100% work first time, you know? Right, so should we clean up this a bit? Anything to do with this that needs, you know, so we really have like kind of like a public kind of API, and one that's really kind of only used internally within the node allocator itself, but we'll keep them available anyway, because it's all internal to the GFX system. But so the basic idea is we publicly just need alloc, dealloc, and defrag. The rest are all to do with the internal implementation and kind of helper functions for that. But we'll still keep them there, obviously. Right, alloc, dealloc. And defrag. Here we go. Just put these above in it. I think that's all right. Yep. So I'll put a comment saying like internal. There we go. Right, so now let's try and use it. So I want to have a node range allocator. So we'll just put it somewhere here. So we'll initialize this boy. BVH node allocator. And what's the number of what's it called now? Number of blocks, number of nodes. So blocks, probably safe to say that's the number of BVH nodes you want to have in total, isn't it? So is that shared? Right. So the total number of trees we want to support is probably 1024, I guess. Because you do one per BVH. Then we also want to have a number of what's the other one? Number of nodes. So the thing is about the nodes capacity, I was thinking about this. We should probably have a maximum number of the absolute hard-coded maximum would be maybe like 1 million. Yeah, we probably want, so what's that, 20 bits? Fit it all in 20 bits for now, I think. Let's just hard code 1,000,000 in there. So that's, well, I want to be careful. Actually, thinking about it. Number of leaves. Max number of leaves. So I think the maximum number of leaves that we want in a BVH, we'll probably never reach that, to be honest. But that's the maximum addressable range, I think. Yeah, the biggest addressable range, maybe. And then we probably want a hard cap. So the number of nodes. See, the issue is what 64 bytes per. Sorry, 16 bytes per node. So obviously that'd be 16 gig, wouldn't it? If you had 1,000,000 nodes. Maybe I shouldn't try and address these limits in places. Let's get rid of ones because it's a bit confusing. So that'd be half a gig, quarter of a gig. Well, sorry. 256k number of nodes times by 4 is 1 gig. Sorry, times by 16 though, wouldn't it? Right, so 1, 2, 4, 8, 16. I think that's right. So it's 32k. That's right. It. Crying out loud. 32k times by 16. No, one off. Right, so 65. Man, I hate this new calculator. Times by 16. That's 1 gigabyte. Right, so it's 1 gigabyte. Yeah, so 1 gigabyte of memory for nodes for now, and we'll see how we get along with that. Maybe on higher end hardware, we might want to push more than that many nodes in total. We'll see. But yeah, number of instances. That assumes you got 2 nodes per tree. Seems impossible to fill that up. So we could probably get away with, let's do 496 for now. BVH tree, number of tree, distinct trees. Let's do 1024 for now there. Right. Total number of no, this is the total number of BVH nodes now. BVH build nodes capacity. Right, so what is the biggest? Okay, maybe we do need to have a separate one. Maybe I do need to bring that leaves thing back. Let's bring back the old constants for a sec. With the new numbers. Okay, so we used to have a leaves, and we used that to make the nodes cap. But that's for a quad. For a tree, No, we'll just work this one out. We'll work this one out with functions anyway. It'll be alright. So got some hard limits there at least. Okay, so the total number of nodes. So drop that in there. We've got to be careful though because there is also a... Here it is, BVH. So the build nodes. What's the biggest tree you could have? Maybe you do need... I guess you could call this total then. No, sorry, it's one megabyte, isn't it? Damn it, I got my things wrong. So it's only 1 meg. Yeah, we can go much higher than that then. So if we support to 1 million or 1 billion nodes maybe. Yeah, so rather than 16, it's 26. One shift left, 26. Damn it, what's this thing up to? Right, that number there. That'd be the maximum number of nodes, and that would be times that by 16. It's 1 gigabyte. Perfect. So one shift left, 26. Then there'll be 1 gigabyte. And then we can store 65k worth of nodes, but yeah, times by 16, and that'll be 1 megabyte. So 1 megabyte per node. So yeah, then 1024 trees, which will get you from 1 megabyte to 1 gigabyte. Perfect. So yeah, I think that's all right. All right. So total build nodes capacity is just the number of the maximum in a tree that you could support. Oh, but you need more because of you need it in a binary. Shoot, you need a bit more. What's the ratio? What number of leaf nodes gets you this? number. Then we can use that leaf node number. It was divide round up +1 or something like this. Yeah, it's not 1 gigabyte, but sorry, I should be clearer. There we go. Yeah, 16 bytes. Yeah, thank you, Psycode, for that. Make it a bit more clearer. It's a good idea. So this is if you have 4 children, the magic formula. So take 1 and then a round up division by 3. So I could probably kind of reverse. So how do I reverse it? Damn it, why are things so bad these days? So let's try and reverse it. Let's do 66. Take 1 plus 3. Divide by 3. Now truncate to 22. Then add 66, because that was the number of leaf nodes. 88. So how do we get back to 66? So divide by 4. That gives you 22. That was that magic 22. Right, so divide by 4. And then it's 88 divide by 4 of that. Okay. Magic. So basically, total, that gets you the number of leaf nodes. Build leaf nodes, where's the total build? Damn it. Right, BVH build nodes capacity, leaf nodes capacity, that is going to be the number of nodes in a single BVH, divide by 4. So capacity, take that, divide by 4. That's the number of leaf nodes. Then you're doing the binary tree one, which is take 1 plus that. Right, that's the number of build nodes in total. So that's the binary tree. If you have so many leaf nodes in a binary tree, the total number of nodes is leaf nodes take 1 plus the number of leaf nodes. Okay, that's all the stuff allocated properly. The shaders are probably not going to compile because I've got some constants in there as well. Number of leaves. Oh, we need that. For what? Morton code. Wait, but the number of leaves would be the same. So why don't we just pre-do this? Is it called leaves cap? So put a comment in there, but we'll hard code it. So it's 65 or 64k worth divided by 4. Take. Run it loud. There you go. That's the number apparently. I think so. Let's try again. 65536 take 16384. Yeah. Neat. Right, so that's the number of. Is that a yeah, it's a multiple of 4. Right. And then it's that as a binary tree 1. Neat. Right, nearly there. So there's the oh, what is that? Call the init function. Right, everything compiles still. Nice. Amazing. So yeah, let's get allocating and see what happens. So how are we going to allocate some blocks and stuff? So we should probably have a block print function. I like the sound of that one. I like the sound of debuggability. That brings well with me. I think you have to cast it to void for some reason, or void star. Or maybe that's in C++, I don't know. Anyway. And then we'll do a bunch of like tab indented things. You know, we could just macro the crap out of this. Equal u new line block. Sweet, that basically worked. Nice. So I guess we can do something like yeah, it'd be right. So I've got this nice block print. Let's find the init. Here it is. So we're going to allocate a couple of blocks. BVH node range block. Let's call it B. Allocate, please. We're going to allocate. Oh yeah. So it's got to be a multiple of 4. So let's do the test where it's just allocating a small number. We'll see how it does there. And we're just going to probably put it in the debugger as well. And then we'll do an exit here. That'd be cool. Now, block ID might be useful, to be honest. So actually turning that into block ID, pretty legit. BVH node or block index. Neat. Yeah, I like that one. Allocator. All right. To be honest, I'm probably going to have one of these allocators anyway, but I guess being an instance is fine. It would just be better if it wasn't an instance for these reasons. But there we go. Yeah, I don't know why it's an instance. Oh. It could be global. Let's run it and see what happens. So what I would like to do is run it, and then we'll go through the debugger and just follow it through, just because we want to double check that it all behaves the way we would like. So we go to run. So it prints out the block. Start 0, end 4. We did ask for 4. But there's a minimum amount that we should allocate, and I don't know. I said I want a minimum of 16. But we've asked for 4, so let's see how that behaves. The previous block in the ID 0, the next is 2. That makes sense because the first one will be 1, and it's had to make a new one, and it's not free, so that's good. So let's take a look at the let's take a look at some of the stuff. So core breakpoint. Let's hop in the debugger. Here we go. So hop in. A bucket index of 0, that makes sense. First bucket, checks the first bucket, not got anything, keeps going until it reaches the biggest bucket. Any minute now. Breaks. Found something, yes. Gets the block. If you look at this block, yeah, the end is all the way over there. That makes sense. Wait, that's the number of nodes. Yes, that's correct. Cool, it is a free block. Neat. We mark ours as not free anymore. There's nothing in the free list. Block nodes count. Nice. Free block. So yeah, it's just start, which is at 4 now. That's all right. Maybe I should change the minimum thing up a bit. Searching over 12 of them is a bit much, maybe. But yeah, block. Previous ID is 1. Yes, that makes sense. And the next is null. Nothing in the free list yet. Cool, that's all right. And it pops it on. Yes, it gets the new bucket index. Bucket index 12? That bounds in it? Right, we're going to relook at that one. Yeah, I was thinking that logic was a bit weird, but I convinced myself it was fine. So that's not good, is it? Run until this one. 26 clamped to 16. And 16 take 4 is 12, yeah. Should be 15. Yeah, we need to up it by 1 if we want 16. Yeah, I'm thinking we should change the bucket thing a bit. You're probably not going to have... How many... So 4 gets you 16, 5 is 32. 32 is probably going to be the minimum, maybe 64. It's maybe... So that's 10. Well, that's 11, isn't it? It's inclusive. Maybe do 128. It's a bit much though. You know, let's go to 5 to be 12. It's fine. But yeah, will we do the alloc? Right, this should be core array alloc. I just realized the bucket index is probably wrong when you want to insert it back into the... When you want to insert it back in there, I think. Yeah, get you 11. No, good. Right, so if you have that capacity, so if you're trying to allocate 4 nodes, it rounds you up to just searching the bucket 64. If you've got 65 nodes that you're trying to allocate, it'll round you up to 128 and you'll search in there. But when it comes to putting one in the free list, you know, you've got 65, you need to go into the bucket before. And you never put one in which is too small. So if you have one which is too small, that shouldn't even go in. That's another problem. If you have one which is super small, it shouldn't even go in the... Where should it go? Well, it shouldn't even show up in the free list at all. It should only... Yeah, it shouldn't show up in there at all. So bucket index... So you always do bucket index +1 when you want to insert... Wait. -1. But if it's so small, you don't want to put... Oh, interesting. So free list... So whenever we do a free list insert, we want to be careful. Yeah, so free list insert, and there's a bucket index there, isn't it? Hmm. Yeah, I guess we'll do that. There's a bit of a problem there, isn't it? Right, another function it is. Small buckets get tagged as an extra space of existing node. So they don't get used, right? Just so you can get back the full size once it's freed. Yeah, that makes sense. Wait, for us, it doesn't... Ah, wait, yeah, because it could be an allocated node, isn't it? Well, yeah, I could just put it on the end of the node. It might not matter, actually, but that's a good idea. Because then I can free the block pointer back. We want to do like a block... Right, I've got a bit of an inconsistency here with some of these namings, actually. Alloc block. Call it block alloc. And then the alloc block. Block the alloc. Right, so the other block one that we want is to well, block the alloc as it, isn't it? Or put it on the free list. Where's that? Here. This code. We're doing it a few places, I think. We're putting it on the free list. So that's an unlink. And then put it on. So you've unlinked it. Put it on free list. We're about some groceries. Good luck, the allocator. We'll jump over still streaming it back. Yeah, it might not be because it's probably getting quite late, but it's getting quite late now. But yeah, thank you for coming by, Allocator. I'll see you in a future one. Good to see you again. Yeah, I'm sure the allocator is going to be done tonight, though. Hopefully, should be good. Right. So how many places are doing this sort of like manipulating this? There's one push on the head. This push on the head is just, you know, you've taken it from the head, so it's not really, you know, you're taking from the head, so that's fine. This code here is next free block index. Right. Oh yeah. So this one we're trying to push on the head itself. Here. Push on the head as well. So there's a few places. So I think we need a function which pushes the block on the head. Okay, this is confusing. If the block is a free block and you're deallocating it, why am I putting it... What am I doing here? Oh, I'm pushing on this next free. Right, okay. That should be the next free block instead. Got it. Right. So you're pushing it on. You've probably done all the other bits as well. Allocator, set free list head or something like this. So you're just taking in the block that you want to set as free list head. Ah. I'll let Psycho answer it, and if not, I'll provide some comments. He said he wants to answer it. Let's see what he says and I'll reply, if not. But welcome to stream, Valbus. Set free list head. So there's a time when we do it in allocate. We do it here. Free block. Now, one thing to be careful about is there's a next free block ID that is retrieved here. And right, if you set as free, oh yeah, it'll do all the linking for you. Yes. So this is all the code we need, I think. Get rid of that comment. Where's the bucket used again? Neat. We go to here, drop that in there. So it has to be a free block. We can only put a free block on the head, on the free list. Free block. So rename that. Right, so we get the size of the block, the number of nodes in the block, get the bucket index. So the bucket index has to be, this is where I've got to do something different, it's takeaway 1. Yeah. So if bucket index equals 0, it's too small. Takeaway 1, so we end up in the right bucket. So it's too small. Maybe we could look at the one to the left or to the right of us. And we could look at the one to the left or to the right of us, just pick one, and move the end. Could you move the start maybe? Or maybe we just don't put it on. And it will be picked up later anyway, when you free it. Yeah, yeah. Yeah, that's a good answer. But yeah, it's quite high level, unfortunately, the memory allocation stuff. But in general, there's three types of memory. There's CPU upload, CPU, yeah, upload memory, read back memory, and GPU only memory, basically. I guess there could be a few more, but that's the basic idea. So the upload and the read back memory can be on GPU, on the GPU card, or on the CPU RAM. It just depends on the configuration you have. Um, yeah, you got to call these like the graphics card API function to allocate the memory. So when you write a custom memory allocator, you basically are making a free range allocator, so with indices. So you don't have pointers, you just have indices into a buffer. So we allocate a whole buffer, and then we just sub-allocate from that buffer with a custom allocator, basically. Yeah, I guess we'll just say, bucket. Block is too small to add to free list. Let's just forget about it until a neighboring free block. A neighboring free block is deallocated and joins with it. So we take one. We take one such that it's a power of 2. You'll be in the next. You'll have 200 nodes, for instance, that will put you in the 2561. But you want to move back, so you're in the 128 bucket. Move back to the previous bucket such that so allocations so that allocations reading from that bucket will always get back a block with more than enough memory. Cool. So that's the next free block. If we have a next free block, get it, make it point back to us, we point to it. Done. That'll be it for now. So let's just get that and hope, patch all the places where we do that. So at the start, allocator, and we put the block in there, and that will insert it in there. Amazing. There's another one. Just gotta find it. Unlock. Yes, that's a take. It's taken from the free list head. This is where I think we can just do no free block physically before this block. We are deallocating. Add it to the head of the free list. Yes. Got to be careful though, because what does this do? Because this calls it now, innit? Because that's going to call it here if it doesn't have a previous free list. Ah, shoot. We don't want that to happen, is it? No, it's fine, isn't it? Wait a minute. That's not good. Ah, shoot. Right, this is fine here, I think. There's another place where we want to... So the dealloc does it. And that's it. Okay, so the dealloc, the problem with the dealloc is that I don't want it to go on the free list. Oh no, it's the next. Perfect. It's not the block that we're freeing goes on there. It's the next block. And the problem is I got it wrong. Wait. You deallocate a block. Yeah, this one's different. You're checking... Damn it. If the bucket index is greater than 0, you're removing it from the free list head if it exists. Remove from the free list head if it exists. So when you're looking for it, you do the same thing, you do bucket index take 1. I think that's right. Okay. Alright, I think that makes sense. Isn't that U16 though? Oh well, I've just got my U16s and U32s a bit wrong. U16 for the node stuff. Probably not an issue, but maybe it's probably better if you just use U16 or U32, but it's fine. Cool. Alright. So give that a run. Yeah, so now let's just look at the... Let's just analyze data and make... So I think we sorted out all our problems. So we'll keep the breakpoint thing around. But let's just so block 0 will allocate it. And then print. Let's allocate a few, right? 2. We'll do 8, 16. We'll do a 4, a 3 and a 4, I guess. 5. So 32, 64. It was 64 where the limit was, wasn't it? 5, 32. Yeah, I think that's good. So if we then print out all those, 6 of those. So we should. Right, so we've got the first. Yes, this block does still fine. This block comes after here, so this is a block index, this is a block ID, and an ID is 1 plus an index. So there's a bit of gymnastics going on, but it's fine. So yeah, this points back to this one and it points to this one. So it's daisy chaining correct. They're physically next to each other in memory. So yeah, they seem to be correct. That's good. So let's start freeing some things and see what happens. So I want to free. Oh. So excuse me. So I want to free, or deallocate as we call it, B4, and then I'm probably want to reprint out B4 afterwards. Got a crash? No. Assert is free block. Oh, I didn't mark them as free. What? Wait, what do we assert is free? Shoot. Ah. Okay, allocate a dealloc. So where does the block stay alive? The block stays alive. Oh, it always stays alive here, isn't it? Block is free block. Let's try that out. Cool, so we've got another block 4 now that we printed out, but this time it's free. And yeah, there's no free list thing here. It is... Right, so we're going to now try and reallocate that same node again. Back out. So that's... I don't know if it'll be possible though. Because if you allocate... You've put... What did you put back in? Yeah, but we've got to be careful though. So you've put B4 back in, which is a 32. So that's going to put you in a certain bucket. And it's got 32 in size. So you've got to be 16 or something. Or allocate a smaller number to get the same node back. Because when you grab a node from a bucket, it's always guaranteed to have more than enough. So we allocate again. This time we'll overwrite B4. We'll print B4 again. And it should hopefully be node 4. We'll allocate 30 this time. Thinking about it, did we get it to join? Oh no, we did get it to join. It'll be fine. Shoot, what happened here? Oh, it must be multiple of 4. 28. It is. Right, so print out 4 again. This time it's now allocated, it's not in the free list either. Right. So it seems to have made a new 7 block now. I think that's going to be correct. But yeah, we can't see it. But the 7 block is going to point to the 5 block next. So if I print out 5, we should see that the previous one is 7. Man, these people. Right, so shoot. I printed out the wrong one. Did I? Oh, I mean 6. Yes, the index got me wrong. Shoot. Blocks data 6. See, part of me is thinking we should have we should have printed out an ID instead. Right, no block 6. Points back to 5. Oh yes, shoot. See, this is confusing because it's got an ID and then the index. Yeah, we're changing that. I'm getting too confused. Right. What? Here we go. Right. So previous one is 7. 7 points back to 6 physically. And 6 is here still. No, this is wrong, isn't it? Look at this end 72. You know, we should reprint out all the blocks again. Well, so this one points to 7. Yeah, I think this is old data that we're looking at. So these are the 2 new ones. So should we also print out 7? No, but this one points back to 6. Why is that? Yeah, that's going to print the same node, isn't it? Right, here we go. So they're saying the next one is 7. But 7's saying the previous one is 6. And saying this one's 5. But then, like, where's the extra 4 bytes gone? That's not good. So I guess when we allocated it, something happened. If when we deallocate it, it shouldn't have changed. Oh shoot. Big problem. When you deallocate a node. Oh no. We shouldn't have gone into these. Right, let's have a look again. Let's go do a core breakpoint. Deallocate. Right, let's investigate this one. Bum bum ba bum. Oh shoot. Step into there. So and then we put it on the free list head. That's it, apparently. So it's deref block. Okay. So it's only when we allocate a new one. So you get a new block out. Right, it's the block we just freed. Right, so we're making a free block to the right. But we didn't tell the next free block to point back to this free block. Maybe we did at some point, but maybe I deleted the code, I don't remember. There's something, maybe I missed it. Yeah, we need that code. It's basically like this code here. So we're saying if there is a next block, physically to the next of free block that is, or maybe block, I don't know. Oh wait, kinda here. Anyway, we'll write it out. Next block. Then get it, make next block point back to free block. ID. Then then else do that. If there's no next free block, then it's the end piece. Cool. Pretty good. So hopefully that does the fix. I just need to remove that core breakpoint and try it all out again. Right, so we deallocated 4, which is 5. I know. So that made it yeah, then we printed out that it's a free block here. Then we reallocated it again. Oh. Why is that physically moved it? Why is that physically moved it now? What did I do? Shoot. Shoot. Yeah, make it point back to the free node. And then this block points to free. And then that points back to us. Right, let's get back in that breakpoint again. Right, so we allocate the node here. Get down to where all that shenanigans or we get the block itself. Yes, the previous is 4 and 5 at the moment. Alright, this is a new free block we just allocated, right? Set later. Yeah, set to 5 and 5. What? Is... So your next is 5. What? Huh? Block take G, GFX, was it BVH, node, range, allocator, blocks, data, 4. Oh yeah, it's pointing to itself, isn't it? When did it point to itself? It's not when it freed it, right? Uh, 4. Oh, they were pointing them to themselves. Oh, that ain't good. Right, let's go back all the way back to number 1. So clearly the change I've made messed it up. Maybe it's the first block. Points to 0. That's fine. So the free block it makes to the right of it, it'll point back to 1, which is the first one we've allocated. And 0 for the next. There's no next, so this is now the end free block ID. And then the next is free block ID. What is free block ID? Why is that 1? That should be 2. Oh, I didn't add a 1. Shoot. So close. Yeah, I forgot to add the 1 to this line. There we go. So we run that. That data should look more correct. So we free the 5, right? It's still pointing to same next and previous node, but then we allocate a new 5, which is smaller. So it had to make a block 8, which we can't see here for some reason. I don't know why it's got to make a block 8. Yeah, so we allocate that. So we free that node back, which is 5, but let's up all these boys and girls. B then a digit. There we go. Just so they match the numbers we saw. Alright. Yes, we freed 5, or deallocated it, printed it, allocated a smaller number, which so it should have reused 5. We put it in there again, print out 5, and then we check the nodes afterwards as well. We print those. So what we see is so we free 5, it becomes a free block. Hasn't changed anything. Still the same, basically, except for this bit is set. It would have had to... Wait a minute, what would have that done? Yeah, there's nothing free. There's nothing free before or after it. So would have just tried to add it to the free list head. Yep. So you take it again the next time around. This time there's now a new free index, which is 8. That makes sense because up here for these guys, when we were just making it before we started freeing them, we made it all the way up to 7. So it makes sense that the next one is 8. So the next one would now be, where is it? Right, so we allocate, the next one is 8, which is down here. Let's get them all on screen now. So the next one is 8, ends at 72, 8 starts at 72, ends at 76. So it's just got 4 nodes in there. So small, it's probably not included in the list, but it's free at least. And the next one in memory is 6. Right, 76 to 6, yep. 100. Right, this one is not free. 140 to this one, but this is a free block. Yep, and this one points back to 6, this one points back to 8, this one points back to 5. Perfect. So that seems to be good. We've probably got a few more little bits to test out. If I said 32, that's going to allocate a new node, and it's not going to reuse 5, right? 5. Yeah, it took over 7, which would have been free. Yeah, and allocate from that. And that, yeah, 8 is now the bigger one. That makes sense. Points back to 7. Points to 8. Point back to 6. Points to 7 again. Yep. And those start indices, and that makes sense. Good, good, good. Right, so that seems to make sense. So I guess we've got to test the other logic where you free one before and after it. And then... So... deallocate 5. Deallocate 6. So if we just print out B5 now, and maybe B6, but B6 should be... We should probably clear some of the memory to be fair, but I think B6 is going to get joined. But it'll be on that unused thing. the unused list. I think we should zero it, not gonna lie. It's just better when we're trying to debug what's going on. Here it is. Core 0 element block. Point to the next. Put on none of that. Shoot, what happened here? Right. I think I might put a pin in it here today, but we're basically finished with this heap, with this custom allocator. So next time we'll just finish double checking some of these issues. Just make sure it's kind of as bug free as we can reasonably guarantee. Just make sure that, you know, all the if statements have been tested, I guess. And then after that, we'll get on to making a build function that builds a BVH and actually dispatches it on the GPU, and probably do another pass over the BVH node structure, make sure that data is all correct, or the structure of the data is correct, because I've done something a bit silly that I want to change my mind on. And then I think we'll be basically ready to start doing some top level BVH or maybe a mid-level BVH. I want to think about this one a little bit more still. But yeah. Right, that was cool. Let's find somebody to rate quick. So I'll next be on Tuesday at 7:30 PM GMT +1 and same time on Thursday. And also a few, 4 hours ago, but next Sunday I'll be on. Thank you so much, Alex. Yeah, it was good. Thank you for coming. Just so damn tired. I should not drink a lot of Coke anymore. Coke bad. Coke bad. Right, I think I might disappear into the night because I'm tired. But thank you so much for coming, everyone. I'll see you on the next one. Check out the Discords if you want to come and chat in the meantime. There's also a YouTube channel. We just posted a new video about BVH construction and how we do it. So check that one out if you're interested. Have a great start to work week, guys. Bye-bye.